that we've established operators for angular momentum and some of their basic properties, we can start to look at the eigenfunctions of these operators. Understandably, it's better to describe something like angular momentum eigenfunctions, not on x, y, and z axes directly, but on axes based on angles. Specifically, we will mostly be using spherical polar coordinates to handle angular momentum and its eigenfunctions. Spherical polar coordinates can look somewhat more complicated, especially when we have to handle something as sophisticated as a del squared operator. Though ultimately what is going on here is fairly straightforward, at least once we get past some algebra that can look a little daunting at first.
So here are our spherical polar coordinates. We have x, y, and z directions, of course, as usual. And the spherical polar coordinates have got two angles in them, phi and theta, and the distance from the origin to some point of interest here. So the relation between the spherical polar coordinates in terms of r, theta, and phi, and the Cartesian coordinates in terms of x, y, and z, is something that we can work out. And explicitly, x here will be r sine theta cos phi. So that is, if we take our vector r here, if you like, and this length r, and we project it onto these axes here, the x-coordinate component here will be this component of r projected onto the plane, so that's r sine theta, and then that component on the plane projected onto the x-axis here, which is r sine theta cos phi. Similarly, the y component will be the same r sine theta, that's the length of this line here, but now projected onto the y-axis, so that's r sine theta, this distance here, sine phi, projecting over onto the y-axis here. And the z component is just r cos of theta, the projection onto the z-axis. Theta is called the polar angle, and phi is called the azimuthal angle. So a strange word, azimuthal angle. In inverse form, the formulas can look a bit more complicated. If we want to figure out r in terms of x, y, and z, well, that's relatively straightforward. That's just adding up the squares and taking the square root to get essentially the length of r, of course. The theta, we have to take a sine to the minus 1, and we can figure that out if we like. This is the x squared plus y squared. Here is the length in the xy plane, and this is the length of this vector here. So the theta is sine to the minus 1 of the ratio of this distance over that distance. And the phi is tan to the minus 1 of y over x. With these definitions of our spherical polar coordinates, and using the standard partial derivative relations of the form like what we have here, so that d by dx would be dr by dx d by dr, plus d theta by dx d by d theta, plus d phi by dx d by d phi, with all of these, of course, being partial derivatives, is the standard form to work out a new form of partial derivatives in the new coordinate system. If we use those for each of the coordinate directions, then we can rewrite the angular momentum operator components in spherical polar coordinates. Now, this can look a little frightening, but it's straightforward. From this relation here, from our commutator, and this one here, and this one here, we obtain that Lx is IH bar times this relatively complicated looking expression in here, and Ly is IH bar times this relatively complicated looking expression, but Lz, fortunately, is rather simple. So I'm not working through the algebra here. This is something you can check out if you want to. But the Lz operator is particularly simple to write down, minus IH bar d by d phi. And these ones are usable, but they're rather complicated looking. And as I say, you can check that algebra if you wish. Now, because we've got such a simple expression for the LZ operator, we can look right away at its eigenfunctions and eigenvalues. Using this expression here for LZ, we can solve for those eigenfunctions and eigenvalues of LZ. It's rather simple. The eigenequation for these eigenfunctions, whatever they are, would be some eigenvalue times the same function, of course. And we have chosen here to write that eigenvalue in the form mh bar. We've not yet figured out what this number is. This is just a number, but we're going to solve this eigenequation to deduce that. Well, rather obviously, you can check that a simple function like this of the form e to the im phi would be a solution of this equation. And we would get mh bar here. We have to do a little bit more work, though. The requirement that the wave function and its derivative are continuous when we return to where we started, that is, when we go around a complete 2 pi of angle here, means that the number m must be an integer. It can be positive, it can be negative, or it can be 0, but it must be integer in that sense. Hence, we find that the angular momentum around the z-axis is quantized, with units of angular momentum of h bar. The eigenvalues are m h bar, where m is an integer, positive, negative, or 0.
We see then that the eigenfunctions of the LZ operator are quite straightforward when written in these spherical polar coordinates. But what about the eigenfunctions of the Lx and Ly operators? After all, the differential operators for those two looked rather complicated in these spherical polar coordinates around the z-axis. Certainly, we can understand that the eigenfunctions of the angular momentum about the different axes are not the same, as required by the fact that the different angular momentum operators do not commute. However, our choice of the z-axis is quite arbitrary. We could equally well have chosen x or y axes as the polar axes for our coordinate system, in which case we would see quite clearly that the eigenfunctions of the Lx and Ly operators are actually of similar form to the ones we just deduced for Lz, but in terms of the angles of rotation about the x and y axes respectively. Hence, the eigenfunctions of the angular momentum operators Lx, Ly, and Lz are not the same, consistent with the fact that these operators do not commute. But the eigenfunctions for each specific one of these operators are quite simple to understand.